to the second panel that we're going to be presenting today out of the three. So first things first, so I don't forget this. We have 4 speakers in this panel. They are Joshua Stein, who's going to be, no, we have 4, wait a minute. We have Joshua Stein, who will be presenting first, then our own Stephanie Davidson, and our own Peter Schmidt, I'm sorry. And also we have Michael Fritz, who looks just like Peter Schmidt, so don't be confused. They are 2 people. It's just that they look very, very similar. Alrighty. So we're all so excited that we were able to pull this together, even with our great attrition and our loss of almost all of our engineers. And hopefully we'll be able to do this again. But it's so wonderful to be able to see the level of investment that different people can bring into this amazing material, which was probably the first material that any one of us ever got to build anything with, because we were allowed to and we couldn't hurt ourselves with it. But it's amazing to see that that clay can go all the way down to the molecular level. So it's really, really exciting. And in the second half, we're going to have maybe a little bit more of a look at the levels of play that the material can go into, both formally and through its interaction with tradition and technology. So enjoy. And our first speaker.
Okay, great. So first I want to say thanks to Laura, Omar, Stephanie, Georg. I'm really excited to be here, and I think you guys should all be excited too. It's kind of amazing what's happening here in Buffalo, and I think people are talking outside the city. I'm lucky to be a part of it. Okay, so really quickly, I've been in my firm Radical Craft. I think it's important to talk about how it's relevant to what I'll talk about regarding ceramics. You could read that in almost 2 ways. One would be updating the traditional, like somehow radicalizing craft, and the other would be testing the technological. Like basically, how does craft radicalize some other trajectory that we're on? I would say that would be a technological trajectory right now. I'll get into this a little bit more, but that's basically where this idea of symbiotic resistance comes from. I'm interested in somehow looking at both sides of that equation. Just to talk a little bit about what my office normally does, there's an interest, I think a very contemporary interest in just trying to figure out what technology means for form, through installations, through public art projects, and then through much larger projects at the scale of landscape or regional infrastructure. And maybe to jump into a quick project, this one was not the first project that I worked on dealing with ceramics, but I think one that was meant to be the most responsible to architecture. So I'd like to start off with that one first. And it comes from, my office is located in downtown Los Angeles, and there's an incredible tradition of turn of the century glazed terracotta tile buildings all over town. Mitch had mentioned that one of the main, let's say, former competitors around the turn of the century with Boston Valley Terracotta was located in Sacramento, California. That is Gladys McBean. Most of all of these would be Gladys McBean projects, where they basically produced all of these tiles. And so I think, let's say, first of all, like I was interested in trying to figure out this technique, which is press molding, which I assume is also what the majority of Boston Valley Terracotta was engaged in the past. I know that's not necessarily the case anymore. But a lot of these terracotta tile facades were done through press molding. And so even then to take a look at what Gladys McBean has been doing as an industry, they're responsible for all of these huge ornate ornamental structures, as well as something that's completely functional, which is sewer pipes. The majority of the business now is in the sewer pipes. And I think this is a kind of interesting conundrum for ceramics and architecture at this moment. These are clearly two different ways that we can think about ceramics as architects. This project was mostly interested in saying, okay, taking a look at that terracotta tile facade, which was mostly done through crest molding, which we could call something which is about 2.5 dimensions. It's kind of like 2.5, 2 plus. It's not quite three-dimensional, it's a deformed surface. What would happen if we produced that through a different technique, which would be slip casting, which produces closed volumes, more or less? And then what could emerge out of that? And I think we know that slip casting, which is the way the toilets are still more or less produced, that number one, they operate as rather complex vessels. So what would that offer as a facade that could be produced out of a series of complex vessels instead of a series of essentially deformed surfaces? How does that move it away from being purely ornamental into something that's ornamental and performative simultaneously? And so this is a kind of host of different types of performances that we could potentially expect out of something that is volumetric and modular. And then these are the two here, the kind of passive air cooling system and the green wall system that we then prototyped. And this module, which was largely designed basically about the flow of fluid between this module and neighboring modules, and then some overall pattern that would hopefully dissipate or remove the kind of browbeating logic of one module over and over and over again. I think that's also a kind of contemporary concern with facade systems in general right now. I think we decided to basically pick a method which was not incredibly complex geometrically, so corbelling, something which deals with courses rather than complex tiling, which would be where you're trying to produce complex curvature over tiles that kind of fit snugly one against the other. We opted out of that and instead chose a kind of older technique, or simply a more, it's kind of like slicing things into two-dimensional profiles. If you can get one course of these modules to run along a curve, and you can just stack those curves. And then maybe what was a little bit more innovative about this then was to say, like, we could have variable molds where we would have rotation, let's say molds where we rotated out different mold halves. One half of which would be responsible for geometry, how it interfaces with its neighbor, and the other half which would be responsible for performance, what it does, whether it's passive cooling or something else. And then this kind of like that, again, that overall aesthetic of trying to eliminate the logic of just one module repeated, but then actually, I think, being more interested, more concerned with how the population of different performances of any one of these modules would start to develop an aesthetic for the overall project. So here, just a kind of like set of different types of performance, like let's say for gray water filtration, I think Brian mentioned the project, which I know through Potters for Peace, which is about purifying water. That would need to be continuous vertically if it were going to be run through gravity, whereas some others, which would maybe be about, there's some others which would not necessarily need to be contiguous. Some which would want to be located closer to the top of this kind of belly so that they'd be facing the sun, some closer to the bottom if they were looking at passive cooling. And then what any of those would start to imply for just kind of aesthetics, for the luster, basically whether or not it's glazed, whether or not it's reflective. Any of the ones closer to the top, which are more about passive heating systems, are kind of asking to absorb more sunlight. Those darker ones in the middle are actually non-glazed because they're meant to be left porous, since those are about porosity allowing water to filter through them. And then how color might also align with that. Some which are just the natural color of the clay body, and others which could be glazed darker to actually absorb more sunlight. And then kind of producing a limited run of prototypes to just test how these things would aggregate without dealing with anything like, let's say, connections at this point, which would be a serious issue. but maybe anticipating them. So you can see that these all have bolt holes, and they're kind of ready to be attached. Structure is anticipated inside of here, but this is not a structural system on its own as a ceramic system. We just kind of like admit that maybe what we're more interested in doing is creating a hybrid system with something like steel or aluminum profiles which deal with structure. And then the ceramics modules are left, let's say, free to do something else outside of structure. And then basically saying like, again, we've got this kind of system of steel profiles, and the ceramic screen then gets to kind of like drape over the architecture, operating almost purely as a kind of modulator of the environment. And it's barely there. I mean, it's a relatively thin profile, so you can barely see the envelope of the entire building, but maybe similar to some of the examples that Miguel showed, there's definitely a loose fit in terms of the program spaces versus the envelope. And then also just thinking about the ways that that both the ceramic modules and larger systems would kind of work through the architecture. I think it was important at every step. So you can kind of see basically the passive cooling system versus something that's more about solar heat gain, depending on the time of the year, of course. So kind of limited set of tests about aesthetics, but I think it was more about like how could we produce a larger architecture given all of these, I'm going to say advances, but it's maybe more like rediscoveries in terms of the way that ceramics can be used right now. And so I'm going to categorize that as almost kind of updating the traditional. It's not entirely true, but then I'm going to contrast that a little bit against some other issues. But maybe in terms of the updating the traditional, this is what we, let's say, this is what we understand to be important inside of ceramics, ceramics performance. And these are some of the issues that Omar listed right from the get-go in terms of what the conference is trying to tackle. Issues of availability, porosity, sustainability, all of these things that we know are inherent in material that I think are important for us to deal with and explore regularly. And then I think there is another way that I think is also worth exploring, which I'm going to call testing the technological, or maybe almost more like teasing the technological. Like, if we're really interested in technology, it's almost like dealing with something as earthly and as material, and as like kind of doggedly material as clay, I think is really important, because that it asks us to deal with technology in a different way. So these are almost more like a list of provocations that could come from ceramics, almost things to needle architecture with. And I find these to be really compelling, almost whether or not we're working with ceramics, but maybe this is what I've learned as an architect by working with ceramics. I'll kind of go through a couple of these through some projects. So this one here was kind of like the first project that I ever worked on. Let's say this is what brought me to ceramics. And it was simply a desire of mine to reproduce something that existed in the world through a material that's felt somehow more precious. So basically the kind of packaging inserts that you find that are less prevalent now, but 10 years ago were quite prevalent. What would happen if we reproduced that in ceramics? And I think I already knew that I had this desire to kind of like deal with an incredibly intense material process that would start to change form along the way. And I think this desire came from me, quote unquote, growing up in a digital education. So all of my studies were paperless. There was no such thing as a kind of interest in materiality. That was simply a function of the era in which I went to school. And I think I understood that as I came out of that, the most important thing to do was to test that against its kind of its evil twin, let's say. So I was looking for materials that would resist in the most dogged way possible. So that's what drew me to ceramics. So potentially everybody here already knows the process of slip casting, but essentially you pour liquid clay or slip into a glass of gold, which wicks away the water. It kind of leaves like a thick buildup. You pour out the excess, and then you let that thick buildup sit. It hardens. You fire it like anything else, and you have a pot that you I love that it has like this association with kind of almost like trinkets. So, like my grandmother actually had a kiln and would produce pieces like this, right? Or let's say with this as the goal, maybe not of this quality. And so the kind of persistence of tradition, of this kind of democratic availability of material, I think is important for us to reconcile with. And I would say this is something that, as architects, we somehow go through phases of ignoring. We're coming out of a phase that was ignoring that for a while. Even this, like this kind of persistence of tradition that a lot of industries are still producing essentially like huge quantities of products, of commodities, through a system that is, more than 100, 200, 300 years old. So the kind of anachronism, I think, is important, like, but there's still something valuable, actually, about anachronism. So, basically, to go back to that project of just producing this thing out of ceramics, I think, like, obviously, once you get that thing out of the mold and you have it as, and get it out of the kiln, you have it as a fired object, it takes on a preciousness that it never had before. It takes on a seriousness as form that it never had before. And then I think for me, I was also really interested in what I could discover out of that artifact that I wouldn't have anticipated had it not been produced out of ceramics. And to almost understand that again as an architect. So to just produce documentation of it through kind of architectural techniques. And then maybe to flip to the other side and say, what happens if we just looked at it in terms of more like dishware techniques, ceramic traditions of dishware. As soon as it gets decalced, it automatically locks it back into its own scale. And so then it kind of begs to have to be inhabited at that scale. And somehow, I don't know why, but it's like packaging and Japanese food goes together really well. But also I think like then if we kind of take that artifact in some seriousness, I think we have to take all of these kind of like quote unquote aberrations that never existed in the original with some seriousness as well. And I think this is another kind of lesson or a provocation that we should take seriously as architects. Just like the impotence of geometry. You can almost misread this as the importance of geometry, which I think is kind of what architecture has been engaged in for the last 15, 20 years. But so we're at a moment where we're finally coming out of that, and I think it's very exciting, which is also why we're interested in ceramics right now. The limitations of geometry over materiality, that somehow materiality still has its weight. This is a kind of cross-section of the plaster mold, and however much you can almost dictate that interface zone between the clay and the plaster, there's always this interior that is produced more through issues of viscosity, surface tension, and less through geometry as dictated by me, the designer. And I think there's also a kind of larger tradition of that, which we can find in just like casting techniques in general. So if we look at the kind of history of reproduction, you see all of these seam lines, which obviously gets to the issue of both scale and complexity, because let's say for this, like the reproduction of these images, like we do have to, number one, take seriously that there is this tendency that reproduction will lead to mimicry. And I think, again, as architects, we need to be mindful of that. What does that mean for our relationship to the past? And then also just the kind of complexity of all of these different mold parts that are required to produce the human form. So at certain points, like that's maybe, let's say, like 10 or 12 mold parts that you would need because of all these different undercuts. But at other points, it could get up to somewhere between the range of 200, 300 different mold parts. And to view that maybe as something that's not a problem, but again, it's kind of a provocation from the process to us as architects, which kind of like segues directly into one of the questions that we had from the earlier panel discussion. Like, what does this mean when we move to larger scales as architects? And I think this issue of upscaling is incredibly important. So that was kind of like the next phase of this project, was to just take that on. What would it take to produce that exact same thing at twice the scale? Number one, it required slicing it up into 8 slices. And then producing these different slice molds, which were 2 parts each, so it produces a 16-part mold, which already is getting pretty complex. But then I basically decided once I had these 16 parts that I would like to have them be repositionable. So there's 16 parts which can shuffle, which means that the precision level has to go up kind of like infinitely. This, by the way, was also done at the European Ceramic Work Center. You'll probably hear that kind of come up as one of the hubs of kind of advancement around the world right now. So there's that one in Den Bosch. There's Buffalo growing. But I think like what happens then when the technique starts to offer the possibility of not just reproduction of form, but actually form generation. Like it produces new forms that didn't exist before and probably wouldn't have been conceived of by me from the get-go. So it produces families of forms rather than just forms. And then something that's particularly interesting for me is the way that this starts to look more like architecture, simply because it's just been doubled once. It went from about this big to about this big, but it starts to have all of these other issues there, like seam lines, ledges, all these things that get closer to architecture. I'm gonna stop. Yeah. Okay. Thanks, guys.
So my presentation is based around the CAFL unit. It's called the CAFL unit, but I'll show how this very specific thing actually relates to a lot of these more general ideas that have been coming up in many presentations. The CAFL sounds like a really obscure thing, but I'm going to leave it as a German term because there really is no proper English translation. The CAFL is part of Kachelofen, and the CAFL is a kind of 3-dimensional ceramic tile unit that's used in the Kachelofen, which is a ceramic tile heater. And because it's different, particularly in German, there's a differentiation between Kachel and tile, which is Fliese. I won't call it a tile. The 3-dimensionality is really critical to it, and I think it's one of the main things that drew me to explore this with some students here at UB in a semester, in a seminar last semester, which I'll show at the end. So in this presentation, I'll show the Kachelofen as a fixture in historic representations of spaces. I'll really show how, although it's made with a small-scale unit, the Kachel, it's really it's of architectural interest because it's a heating system that's very experiential and has a very particular presence in space. And of course, it conditions the temperature of space. So we'll look at briefly the Kachelofen and its relatives, historic typologies of radiant heat, which there are many. Construction step-by-step of the Kachelofen, formal lineage of the Kachel unit back to medieval times, traditional Kachel fabrication, and then revisiting the design of the Kachel unit, looking at some projects that students here did last semester. So very briefly, the Kachelofen is part of a very wide family of very low-tech heating systems that date back centuries. I'm sure you all know of the Roman hypocaust, and this is a kind of direct offshoot of that. There are very similar Finnish or other Scandinavian, Russian models, the Korean undal, the Chinese kong. These are all really similar. I focus on this because it has a very specific way of handling ceramic, so I'll focus on the Kachelofen. This is an example of really simply how the Kachelofen functions. So it's most usually a wood-burning fire in a firebox, and instead of like we know in fireplaces, instead of the exhaust going straight up a chimney, that exhaust is trapped in a kind of labyrinthine, sometimes really long flue, which is made with masonry. So the idea is that this exhaust, not just the fire, is a valuable heat source. So it's trapped in this system for longer, and it's trapped specifically in a masonry system because masonry has the potential to absorb that heat and release it slowly at a temperature that's comfortable to the touch. So again, here's another example of just how simultaneously simple and elaborate this system is. Basically, smoke it tumbles, but eventually it wants to go up. It is drawn out of buildings, wants to go up, and it's drawn out by cold air as well. There are calculations to know really how long that flue can be before the chimney draw, loses its power and the exhaust is no longer forced through. Of course, it's not a good idea to have a flue run that's so long that the smoke becomes stagnant and puffs back into the room. But that's the general principle. It's very simple. And in the studies that I'll show you at the end of the presentation, this is just an example of how the students started. They looked at various precedents just to see how the system played out historically in space. So what is the impact, or what is the potential impact, or what has the impact been historically of this type of heating system on space? With the Korean undal, very similar to the Roman hypercross system, there was a floor buildup with this flue run, and the floor was heated. So we think of radiant floor today as this fantastic luxury. It's actually it's been used in very low-tech, more primitive ways for centuries. So I just wanted to go through some historic representations because I find it so fascinating that how prominently the capital as a heating system factors into or shows up in historic representations of space as a spatial thing. So this is a painting from 1909. You can see how, and this is very common, that a bench was built around this colloquium. Again, a bench built around just to enjoy the surface temperature that in Fahrenheit goes up to pretty much maximum, typically 100. Even older representations of people magnetized to this heat source huddling around it, and in manuscripts. So you can see, even in these representations, that the cathode looks a little bit funny, like it's decorative, but it somehow wants to have a three-dimensionality. But why? This is a kind of 1950s, 60s image, and there are these concave indents that seem a little bit inconsequential. Here, it's from, the 1800s, very straight up, decorative, merging into the wallpaper, celebrated as a pretty object in the space. Again, the relief here is sort of shown, but it doesn't have performative dimension in this example from mid-century Germany. A Russian example, and they tend to get extremely ornate and decorative in the Russian typologies. In Austria. And here again showing how some of these were built to really invite direct physical interaction. So then something also that I find is interesting is where the cathode oven is so common in history, it becomes something that people just assume is in a space, and they're still built today, and they're often even parts of doll house kits. So this is a contemporary showroom for Kaffeeofen in Germany, and part of the impetus of the seminar last semester was seeing contemporary Kaffeeofen and really a revival of interest in this heating system medieval artifacts from Germany. And the German sort of speaks to the scale, so a Becher is a cup. These are called Becher cackles, so like cup or cup tiles. These two top, so different types of vessels. And if you think of the images that I just showed you, the difference is so dramatic that the three-dimensionality and the capacity for these things, and the suggestion that they could, that they have a much different relationship to fire and mediating the heat compared to the flat tiles is really extreme. So this is from the 14th century, another three-dimensional top kachel, the Kugelkopf, and then Spitzkachel. So this is particularly interesting, the Spitzkachel, because in building up the original Kachelofen, this particular tile recognized that when you started to build them up and create, as they were, domes, they don't really have very explicit examples of how they were built up, or drawings like this in museums and things like this, but the Spitzkachel shows that there was a recognition that there was kind of an overwhelming amount of mortar or binder, clay mortar, and that these three-dimensional forms needed to be shaped and engineered a bit more so that they were more, that the heaters were consisting more of these kachel and less of this binder. So again, Napfkachel, Napf are little bowls for animals. And then the Rechteckachel is also a very interesting development from like a Schüsselkachel or the Becherkachel, where these were obviously thrown on the wheel traditionally and then manually pinched, so that again they could be more, that they were a bit, I say it sort of lightly, engineered to fit together and build up into this particular form, which functioned as a heater. So then, these very, very old shapes became over time this. And so what started as where the depth in these cases was an actual function and people used that depth, not only was it a mediator of the heat, but people put things in these actual little containers and warmed their hands inside. Suddenly, at some point, they just became decorative relief that characterized the Kaplan for centuries, really for the last centuries. So the students looked at, for example, really why, so looked for a logic behind some of these old Kaplan forms, and looked at how they figured and played a part and performed in these heating systems, and how the exhaust smoke related to them, how they mediated heat. Again, more examples showing also how they were traditionally made. So again, there was a critical moment where this volume turned flat and any kind of relief became more decorative than functional. And these are examples of Kaplan on websites currently in Germany, kits that can be bought. So there are two directions. Either the Kaplan often is seen as a very traditional object, and the Kaplan itself is not really investigated anymore for its technical properties, definitely not for its structural properties, or even for its haptic properties. It's seen more or less as decorative, and it's kept that way, or it's dropped, and a lot of contemporary Kaplan are just plastered, and the masonry is invisible. So this is a project here in Buffalo where we built one of these, and we were very interested in the Kaplan, and interested in maybe investigating the Kaplan in this project. It became obvious very soon that it was so labor intensive really simply articulated through a really long loop. So the firebox is here, it's insulated off of the floor so that all of the heat is forced up and out. And the smoke is drawn up through a chimney here, but first of all, there's a hole in the side of the firebox, so it's drawn through this entire bench and up. That bench is clad with a kind of refractory clay panel, precast, and that is a kind of material that it becomes fired over time as this unit is actually used. And then on top of that, there's concrete board just boxing in the chimney basically, and this entire bench, this is the sort of performative radiator really of that system. So these images show the guts or the interior of this system. You can see these boards in relation to the firebox, the construction process, how it was built up. The cladding in this case, very disappointing because it's not relating to the fundamental system. It's a cladding just like a ceramic cladding is also in contemporary capital, although this one is so big it was too expensive to use ceramic tile. So again, I mentioned capital that are made currently here in Guelph, Ontario. This one was trained in Austria and showed the students directly how these really it's kind of like a religion. There's a very strict orthodoxy in how these are built, the whole capital system. And the interior is completely the purview of an engineer. So that's interesting too, that they're two different systems divided by two different experts. The capital system is something that can be taken apart because it uses clay mortar, which is soluble. The craftswoman Justice Steinhauser gave a demo of how this little assembly could be taken apart and then put together again. Just like Joshua was describing, she uses press molding. You can see here the mold. She actually doesn't make them herself. She buys them, and they're very flat. She rolls out the clay, very traditional technique. This is really how they've been doing it for centuries, except for the extrusion machine. These were, of course, made manually before. These are the fins that make this otherwise very flat tile three-dimensional. So these fins are critical in differentiating a tile from a flisa from a couple or a tile from a couple, because within these tile volumes, mortar or clay mortar can be packed to contribute to a higher thermal mass for these and adhere to the actual functional system within. So then jumping really quickly through this course, so the objectives really were to study the capital opening in relation to other related radiant heating systems and historic precedents, to study and catalog historic medieval forms of capital, and it's really difficult to find these in English at all. To study and catalog historic forms of capital in relation to heating systems in which they were embedded, and then to fabricate a full-scale capital in its historic form, just to get a physical sense of how these were made before actually designing anything. And then the ultimate task was really to develop a new formal direction for that capital unit, responding to forming criteria, the variability. So Joshua mentioned this too. I think the capital form should be a variable unit and have the potential to perform in different ways within the heating system, not just a single repetitive tile, but something that could be used in variations packed with clay, left hollow, turned with a concavity toward the room, turned with a concavity toward the fire, all with certain performative and haptic logics. The assembly, so in this case, I really asked the students to develop a system where there was no difference between the interior buildup, that functional masonry, and the exterior cladding. So that ceramic module should be self-structuring. Obviously, it's not supporting anything but itself and performative, but the assembly should be thought through. And then exhaust, so there should be thinking about how the exhaust, that heat source, the smoke, filters through these units and then radiates into the space. And then, of course, the interactive potential. So what is the presence in the room, and again, exploiting the potential of the So every student team started with a precedent. In this case, I'll show you just 3 quickly examples. They studied the black cackle and are really informed heavily for design. They looked at Jessica's method, and they developed a fabric formwork. In this case, it's really interesting because they didn't start with clay. They started directly in making a mold. So they made this frame and used fabric formwork, which under tension bulged in a way that they sort of pre-imagined, and ended up with variations of the bulge. This was an interesting mold because unlike many molds, it was a mold where the pieces could be swapped out because of this mitered corner. Typically, for anyone who's worked with molds, you know that they have registration marks, and a mold and its relationship, the relationship of its various parts is really specific to that mold. But in this case, these were not. The mitered corner, of course, is really not stable in terms of how that mold locks together. It doesn't lock. So you can see they had a really elaborate strapping system because the weight of the slip was also very heavy. So here's an example of a module, a 3-dimensional module made with just one bulge, the interior of the mold. This is made with pottery plaster, very simple. The slip being poured in, it was too heavy to pour out. Here you can see, it's so enjoyable to see the students start to really observe the physics of the project, and that moment where the skin is forming and slip casting and peeling away from the plaster, although it's filled with liquid slip. So as I mentioned, it was too heavy to pour out. The entire skin inside collapsed when they tried to pour it out, so they actually had to scoop it out with bigger bowls and then smaller bowls. So there it is hollow, releasing it from the mold, and here's a piece of greenware not yet fired of just one of the modules, views from various sides. I'll just flick through it very quickly. So these were first attempts, so they're not, they're full of questions and challenges. So just very quickly, their logic and drawings for the fabrication, and then they were asked, because of the scale of these units, didn't make a build-up, but the other students built up 4 courses around a firebox. So here is their explanation of the assembly, and in their case, they wouldn't actually, one of these they presented as housing even the firebox, so this could be built up as a solid unit. In the next case, this group of students started with the traditional technique of actually throwing and pinching the 4 corners of or a Schüsselkachel into a Nachtkachel or a Rechtkachel. In terms of assembly, to try to avoid the predominance of that clay mortar, they started to just try to pile them, but moved quickly into slip casting and made through routing and then manual sanding a model, which was invested. And then again, these are just glimpses into the very standard slip casting method, which these students did really often for the first time in this class. So often they had many molds going at once so that they could produce enough to make an actual build-up and test their assembly ideas empirically, see if there were problems, and then adjust. In this case, they wanted to fuse some together again to try to make this variable unit where there were sometimes 2 units connected to make closed shells. So they would have to keep some parts moist and allow other parts to get dry and stiffen so they were stronger. Scoring and slipping, very conventional way of fusing. It's done also by Jessica Steinhoff, fins, scoring and slipping the fins onto the faces of the black couple. And then these were fused to make units. And in this case, there was also a hole often here, depending on how they were drawing the exhaust. And this particular unit, this is how they built it up. The firebox would have been here. This would have been the entry point for the exhaust, and then these actually would have only acted as buffers on the edge. They don't channel any exhaust at all, so that's just a glimpse into the variability. Can I just show the last one, Laura? Quickly. So these are in space, different, the behavior a very direct working from precedent. But what's interesting about this project is they inverted that form, and whereas this was the top, this project was viewed as not succeeding because it lost so much thermal mass. So obviously when we turned everything into shell, where was the thermal mass? Where was the masonry? There was somehow an objective, get rid of the mortar, but mortar is very useful and performative in holding heat and radiating it. So in this case, flipping it and making the big mouth of this bowl solid and also concave so that it could be packed with clay mortar, allowed them to think more about where this mortar, which is essential again in the system, could be displaced and used strategically without compromising the tight assembly of the units. So here's an example of packing up. I mean, the clay wasn't the right clay, but just to see. And so they tested different ideas of assembly with this unit and actually worked at putting some together. And very similar to the last project here, they built it up into 3 courses, and the holes are signaling where, this is the end of that channel, and then it would move up into the next course, which isn't built. So they drew this sort of variable unit showing the pockets in which the clay mortar could be packed, the assembly around the firebox, air intake and chimney, and then the final set of units. Thank you.
My name is Peter Schmidt, and originally I was coming here with Mike Fritz, who is another sculptor at Boston Valley Terracotta, where we both work. Unfortunately, Mike is snowed in today, so I'm going to try and do a little bit of both presentations and hopefully not take twice the normal length, so we'll see how this goes. So I currently am employed at Boston Valley Terracotta as the manager of digital design at the plant, and I got my start working with Boston Valley at University of Buffalo as a graduate student. I was placed as an intern at Boston Valley, where myself along with several other researchers from the university, worked closely with craftsmen at Boston Valley to attempt to integrate digital technologies that were being studied at the university with existing craft skills that had been heavily practiced at Boston Valley. So we've already talked a lot about terracotta, so I'll try and gloss over the intro a bit, but this is some stuff that's more specific to industrial manufacture of terracotta that hasn't really been covered too much up to this point in the presentation. So terracotta really got its start in architecture in the 19th century as a cladding material for steel frame skyscraper buildings. Here we see a sketch done by Louis Sullivan for one of the guarantee tiles, which is on the guarantee building in downtown Buffalo. So typically, the architect would have a lot of say on what sort of ornament he wanted placed on the building. And so here we see Sullivan, who would give his sketches directly to a sculptor, Christian Snyder, who would carry out the details in 3 dimensions. So here we see some images of sliding beam sculptors around the early 20th century. They are in the process of making individual parts, which after the parts are created, they would be cast into plastic molds and pressed for reproduction. Here we see a traditional assembly as it's being constructed. So the whole part would be made and then sliced up into individual segments for molding and reproduction. This is the same process happening at Boston Valley Terracotta only a few years ago. So here we see a large assembly for the county courthouse that is made at full scale by sculptors in a very traditional hands-on process. We can see the sculptors working with the clay, dividing things up, and making all of the models that would later be used to derive parts. Again, here we see a large sculptural positive for a guarantee tile that is taken from, if you see it on the right there, there's a smaller version of the tile that's divided up with a grid to be scaled up and reproduced. Once the models have been segmented and molded, they're then loaded into a traditional kiln. Here we see a beehive kiln from the late 19th century. While Boston Valley was still doing some traditional techniques, a lot of it had already begun to modernize. So here we see a modern kiln in use at the plant, alongside very traditional handcrafted methods. So here we see someone who is hand packing clay into a mold in order to get the proper compression and finish of the product that they're looking for. So here is kind of where Boston Valley was pre the intervention of the University of Buffalo. Students and faculty from UB were able to bring several different skill sets to Boston Valley that did not previously exist there. Boston Valley had a rich tradition of handcrafted sculpture, very detailed ornamental reproductions, but was generally lacking in digital know-how. So researchers from the university were able to bring digital modeling in the form of Rhino, ZBrush, skills which are typically developed within architecture school, along with scanning, multi-axis CNC, and several other rapid prototyping techniques that are used here at the university. This is a photogrammetry model generated from a series of pictures. This allowed the sculptors across from Boston Valley to interact directly with a sample without having to always lug it in and place it on their table to work with it. So in this fashion, by taking a series of pictures and using photogrammetry algorithms, they can work with and interact directly with a three-dimensional model that has the same textures, colors, and forms of the shape they're trying to reproduce. This is very important because the shapes which were being reproduced almost always were damaged, hence why they needed to be fixed and reapplied to the building. So the combination of softwares allowed us to make changes, edits, and work with the models the same way a traditional sculptor would push clay around on a table. They had that same ability to move things around in a much cleaner three-dimensional modeling environment. And these were skills that were brought from university researchers and taught to traditional sculptors who in many cases had been working at Boston Valley using their hands for the last 10 to 15 years. What we're looking at here is the first project that I worked on as an intern at Boston Valley Terracotta. This is the restoration of 150 Nassau Street in New York City. This is a 25-foot high terracotta angel, which before we undertook the project was in a relatively high state of disrepair. As you can see there, the steel straps are attempting to prevent this from falling off the high rise and onto the sidewalk, hence why it had to be taken down, remade, and then restored back onto the building. When it originally arrived at Boston Valley, it came in this form. This is what we traditionally refer to as the sample body bag, where you get a large duffel bag full of broken bits that you then have to attempt to puzzle back together in order to recreate the piece that has been sent to you. So here are some more individual parts as they're arriving at the facility via the contractors. For documenting of the part, we employed a lot of new digital techniques. So here we see structured light scanning, which is employed to take the head of the structure and by projecting a series of black and white lines across it using a monochrome camera, and a high-definition projector were able to read the depth of field, and through rotating the sculpture, you can fill in the holes, undercuts, and recreate a scaled mesh that very accurately represents the stone that's on the table in front of you. For other pieces, we weren't always able to get the sample in one piece to bring it into our shop and scan it, so we again applied photogrammetry while it was still on the building. So before the contractors started pulling things off, we were able to go and take photos of what was happening, and that allowed us to begin to build assemblies with the pieces that we couldn't piece together from the various bits of rubble that arrived in Buffalo. So here we see an assembly starting to come together. This is the kind of hips down area of the angel as it's being filled in with different forms. So everything that is in blue here is the mesh, which was generated using photogrammetry. The darker gray on top is rhino models that were built on top of the mesh to ensure that we have proper joints going in and everything was accurate in dimension so that it could be aligned back up at the end. And the white are pieces, so the base piece, that all was something that we three-dimensionally scanned using structured light, and we're able to combine all of those different data acquisition techniques into one comprehensive model that allows us to get kind of the best look from various places at the statue we're attempting to document. So here we see this is the three-dimensional model starting to come together, and the final dimension sculptural piece, which in total is 25 feet high and has something like 72 unique parts in it. And all of these parts were able to be accurately cataloged and recorded thanks to the skills that both the craftsmen and UV researchers brought to the table. The craftsmen had a deep knowledge of what they needed the software to do for them. They knew where joints had to be placed, where the mortar needed to go, where steel was going to be put through. And the UV students were able to guide them toward the proper tools to use and digital tool set that will allow them to make what they already knew how to do with their hands happen in a more digital form. So once the digital model was complete, we began segmenting it up for reproduction. So here we're taking the head and shoulders and building large plaster volumes inside of that that would act as backups to hold the parts while sculptors went and reapplied. So here this is a wooden version of the backups that were shown on the slide before. So you can see there are some laser cut pieces which give the sculptors an outline of the joint to ensure that the accuracy of the model is going to be transferred into the final built part. There's another close-up. So these are 1/4-inch plywood, which can be fairly easily cut using the laser cutter that Boston Valley purchased with the help of operation skills that the UV researchers gained in the School of Architecture. So here again is the segment missing that we're looking to recreate on this table. And here are the sculptors beginning the backup modeling process. So basically they're just lumping in plaster to fill space until they have everything masked out, and from the masking stage here, they then begin to apply clay and do a fine sculpt on the more intricate details of the angel itself. So here we see that head and shoulders area. You can see a bit of the white foam and massing on top, and the finished sculptural details more down toward the bottom area as a series of sculptors worked to recreate the forms that were previously existing. Another thing that's important to realize is that the forms can't simply be copied due to the shrinkage of the clay. You have to model it 8% larger so that when it shrinks back down at the end of firing, it maintains the original dimensions. So all of the sculptors, you can see some of the pieces sitting next to them. They have to measure it with a 1-to-1 ruler, and then when they go and sculpt it, they have to inflate the dimensions by 8% and apply those to the model. And here we see some of the backup and some of the wing parts as they're being taken apart. Each block is able to be removed individually thanks to the planning of the joints that we're able to do with the random model. So as molds are being made, individual blocks are being pulled off, put onto a mold porous table, and a 5 to 8 part mold was made off of each piece depending on the relative complexity. And here is the lower section, so from the hips down. The assembly was so large that we didn't have space to build all at once, but because we're able to take the same laser cut templates for what is above the hips and what's below the hips, we were able to ensure that the pieces would in fact go together after everything was fired and brought out of the kiln. So here we see the entire assembly mocked up at Boston Valley before being shipped out. The architects and contractors wanted to come down to the plant and inspect it to make sure that it would in fact fit together when they got it 20-something stories up in the air. And here's the before and after image. So within 2 years, all 4 sculptural angels, one on each corner of the building, were all successfully taken down and replaced with historical reproductions. So here is a project that we recently undertook, looking at the new digital tool set as it's applied to a site in St. Louis, Missouri.
We had spent the last 2 years developing a digital workflow at Boston Valley using new tools, scan data, and digital modeling. We were looking for an opportunity to bring these tools into the field. When we were approached with a 1.5-day survey window for a project in St. Louis, we knew our chance had come. We had coordinated with the contractor prior to our departure to arrange access for the areas that we were responsible for surveying. However, site conditions are never what we expect. Our tools, though, gave us an edge. Using a laser tape and photogrammetry techniques, we could reach out and collect data from places where access and time were limited. The result was a fully interactive mesh or digital sample with amazing detail. From border joints to surrounding conditions to picking dimensions from the mesh, we could build models directly from site scans. And if we could achieve this for a spark replacement, why not think bigger? Why not an entire elevation? Digital documentation practices bring us directly back to site, even when we've left the site. The technology is changing, our tools are changing, and our craft is changing. Our relationship with historic structures is entering a new era. Not only do we intend on being a part of that era, a part of that change, but we also want to be the ones who are driving it.
Okay, so what we just talked about was about half of what Boston Valley does. Typically, we do restoration work as well as new build construction. So, looking a little bit at how we can apply other digital technologies to both sides of the equation here. What we're looking at now is a guaranteed building tile that's being routed on UV's 3-axis router. A partnership with UV allowed Boston Valley to have an opportunity to test drive certain technologies, so they were able to see and experiment a little with things like CNC manufacture before fully investing in the technology. And once invested, we're able to create complex assemblies like we see here. There's column details, railings, and cornices, which the assemblies and the structure could be broken down, and once the models were built, they could be easily CNC'd. So here we see the 5-axis router of Boston Valley, which is 5 foot by 5 foot by 5 foot work envelope, and capable of quickly reproducing the information that was digitally documented in the drafting process. So here's the finished column as it's coming off the CNC machine, and it will be either A, sculpted on, or B, it can be directly molded and pressed. So another project that I worked on with Boston Valley was the New York Townhouse, where we worked with Normal Projects, architecture firm in New York City. The goal of the project was to create a complex facade where the facade itself would give the impression of a water droplet hitting a surface and rippling out. So the architect wanted to have sloping panels which would convey that gentle gradient. The problem with the sloping panels was it presented a very large number of unique shapes, which is typically the enemy of any industrial manufacturing process. When the architect had initially sent us a set of drawings for what he wanted, we immediately took one look at the PDFs he sent and realized that he used a Rhino model to build it, so we asked him to send us the Rhino model, and from there we started a dialogue of collaboration between manufacturer and architects, where we were bouncing back ideas and refining the design digitally using both the design input of the architect and the traditional know-how of the industrial craftsman to attempt to get something that's manufacturable as soon as possible in a design process. So here we see the initial schematic design changing for the construction. Each color represents a different slope, which is put on the building to create a gradient. So the different colors are starting to break down into families of parts which can be reproduced. And this is an image of the jig, which was developed using laser cut templates to take a single shape and cut it into multiple shapes. This is the die, which was custom CNC milled out of steel to fit onto a repurposed pipe extruder for terracotta drain pipe. And this die allowed us to manufacture the specific shape that the architect was looking for. So the shape there is a result of collaboration between feel and interact with what had previously been an all-digital workflow and process. So it allowed him to experience the terracotta and see the effects of the cutting and what was happening as the parts were being extruded. Here we see a couple different samples for glaze, which would also be tested on the project. And finally, a breakdown of the entire process from the custom die, which is being made, to a large run of extruded terracotta being cut into smaller workable segments, each with individual slopes to be later placed on a tracking clip system that would allow them to create one single facade that displayed a large number of unique shapes, showing the gradient pattern that was the original design intent. So the first projects that we've looked at have all been jobs that Boston Valley Terracotta was paid to do. The last project I'm going to talk about is the opposite of that. It was my thesis project for the University of Buffalo School of Architecture. Based on my work as an intern at Boston Valley, I quickly realized that architects and manufacturers needed to work closely together. The collaborations that we had previously done had demonstrated that, and it demonstrated the benefits of architects and manufacturers working closely. However, there was often a lot of, call it telephone translating that had to happen, where both sides thought they were talking about the same thing and nothing really lined up. There were lots of hand-waving, whiteboard-centric conversations trying to convey to the other side the architect's intent or the industrial manufacturer's feelings on what could actually be made. So for my thesis, I undertook the task of trying to create a digital tool that would bridge the gap in between architecture and manufacturing. So I proposed a custom wire cutter for the process of extruded terracotta. When talking to the craftsman at Boston Valley Terracotta about my idea of wire cutting, I was initially greeted with a lot of skepticism, and once I got past the skepticism, I was given a large number of general descriptions, which were very difficult to quantify in numbers. There were a lot of qualitative descriptions for how the terracotta feels and what happens to it, which is helpful, but not great when you're trying to design something that is computer software driven. So I needed to associate numbers with all of the variables that were qualitatively described to me. So I broke it down into a series of tests here. We're looking at the coefficient of friction as compared to the density of terracotta that would hold the terracotta in place and allow it to be wire cut. The next variable I had to test was the force required to pull a cutting wire through a block of extruded terracotta, which is much harder than typical sculpted clay or plasticine. So the cutting force relative to the diameter of the cutting wire had to be also documented and cataloged. You can see here, this is a plywood jig that I built using a force gauge to accurately calculate the cutting forces of different moisture contents for terracotta, because as the terracotta dried, of course, the cutting properties changed, so that variable also has to be cataloged. The next variable that I had to test was the deflection and breaking strength of the wire, because terracotta is a very densely packed, in a very densely packed form when it's extruded, so it actually becomes an issue of the wire not being able to withstand the cutting force or deflecting too much under the force exerted by the terracotta. And in order to accurately cut, I had to program a deflection matrix that would keep track of the amount that the wire was bending at all times and compensate for that in the movement of the cutter. Once all of the variables were cataloged, I then moved forward to create a plugin for Rhino that would expose all of the variables that I myself had documented to anyone who was attempting to design with Terracotta. So an architect could simply download the plugin, and they would immediately have at their fingertips the modulus of elasticity for the average cutting wire, the strength of Terracotta, what your coefficient of friction was going to be. All of the various tests could be easily seen in one graphic user interface. Step 2 of the process was to design the actual machine to do the cutting. The machine itself is a 4-axis wire cutter and breaks down into a conveyor table, which moves the clay along horizontally to integrate within the larger scheme of the extruded terracotta workflow at Boston Valley Terracotta. And it also serves to control movement in the X direction, similar to an X gantry would in a typical router or CNC application. The Y-axis allowed the table to move left and right. The Z-axis pulled the wire up and down. And the C-axis controlled the position of the wire so that it could be rotated 360 degrees in any direction, allowing for any number of ruled surfaces to be created using the 4-axis wire cutting system. So this is a little demo of the plugin that I wrote using very simple curved geometries in Rhino. You can create fairly complex forms. So here, the only inputs that have to be designed are the shape that you want the wire to take. So the blue curves that are being selected are the cutting profiles. And then the gray surface is the extruded shape. That would be the die. That would be the base for the extrusion. From there, you can generate all of the G-code that will run the machine. So that's what you see in the upper left-hand corner there. And it also runs all of the optimization tests to ensure that the wire will actually be able to cut properly for that specific profile given the input curves and diameter of wire that's being used. So it essentially will give the designer access to all of the variables that they need to design the terracotta in a very efficient manner. So here we're seeing one of 3 tool paths being cut on the wire, and all the simulation happens real time in Rhino, so you can run it and then watch as the extrusion is fed through the wire cutter. And as each cut is made, it's subtracted out as it would be in the typical process. So you can see the final result is a piece which has a sloping cut and 2 end segment cuts to ensure that you get the proper end length for each end. So your overall dimensions can also be cut using that. And here we're looking at the controls that operate the various axes of the machine. So here we see 4 different servo driver, 3 stepper drivers and 1 240-volt servo driver, along with all the cutting calculations that had to go into making sure the motors themselves were strong enough to deal with the forces that the terracotta was going to be placing on them. So we see torque curves for various steppers also. And here we see the gearbox and servo motor that controls the x-axis, so the motor powering the movement across the table. This motor had to be substantially larger than the other 3, which were operating the C, X, and Y, or C, Z, and Y axes. And in order to justify this purchase of a larger motor, I had to do a lot of calculation here, not probably most important of which being the very bottom calculation, the force per dollars calculation, which helped me justify it to the people who are actually paying for this system. And here we see the gantry, which itself was a very complex assembly of bearing blocks, gears, pulleys, and servo motors. After several times of me going through and completely redesigning the model from the ground up, because I had to change the servo size or had to scale up my bearings, I eventually made a parametric model using Grasshopper, which allowed me to place all of the parts parametrically and continually calculate the forces that are being generated as I make changes to those parts. And once the machine design and the plug-in interface were both set, I undertook a few simple design charrettes to kind of test out the process and see what I can do using very simple cut-ruled surfaces. So here we see the same object that was simulated, a simple A extruded shape that can be cut with a single sine curve and then applied across at the side to create vertical shading. This is just a quick 15-minute schematic sketch. Here we see a sine curve and a zigzag shape, which can be placed together on a track and clip system, which give a facade with a variable amount of depth and a certain texture to it, as well as a chamfered corner condition that can be introduced. And here we see multiple tool paths, so cutting all 4 sides to create various column conditions, and what you can see at the top sort of begins to resemble what would be considered a more traditional frieze that would happen in, or has been done before in older styles of architecture in another little design sketch. Okay, that's all I got. Thank you. Also, Mitchell would like me to pimp a class that we are teaching. It's focusing on CNC design and attempting to introduce students to the variables required to build your own fabrication machines. So servos, stepper motors, CNC control software, things like that.
When is that taking place?
Next semester.
You're all set.
So Josh, Stephanie, will you come up, and now we get a question and answer session for everybody all together. And I have questions that I can start off with, but maybe I'll just open it up to the group. Does anybody have a question?
What's the next step with your exploration?
I don't know. I mean, I think it was pretty ambitious for a seminar, but obviously, I think the next step would be to construct a functional oven so that we could do more empirical testing similar to Brian's, not at the molecular level, but just like testing the surface temperature to see if these hypotheses would work. We had Martha as a sort of performance critic for one session, but I think then just one system would need to be chosen and really optimized and then built and tested with fire.
I have a chimney fireplace retrofit that I'm interested in commissioning. Just takes heat as soon as I write it.
Does anybody have another question?
I have a question. This is mostly geared towards YouTube, but I'm sure you might have something interesting to say about it as well. I was interested in both of your both ornamental and performative. I think it was you who said. But I'm just interested. I'm interested in asking the question, like, where does that come from? Does that just come from a desire to sort of make two things that perform two different functions, like come together? Like, can you unpack that a little bit? I'm just curious.
Yeah, I mean, we'll probably, I can see that desire in your larger projects as well. I mean, for me, I think some of it is just kind of disciplinary. Like, I think in architecture, there always needs to be some kind of response. You need to be responsible to some kind of performance criteria, right?
Yeah.
Like, part of that is that let's take the example of the ornamental terracotta tile. So it's hard to justify doing that nowadays because of something called value engineering, which means that basically anything that can get cut from the budget will get cut from the budget. So if you can figure out a way to make something that is decorative but is still performing some kind of function as a necessity in the building, you have a higher chance of keeping that in there somehow, right? So, I mean, I think that's in a way that's kind of cynical, but also I think that's part of the game of architecture. I mean, that we somehow have to reconcile both of those demands or issues. So I also think that the minute that it's decorative or ornamental, I think we have to somehow reckon with something historical as well, because there are huge traditions that exist. And so I'm also interested in that. Obviously, your work is inherently everything that you've been doing at Boston Valley Terracotta somehow has to reckon with the historical as well, which is, I think, makes it really interesting.
So, yeah.
I think Stephanie wasn't.
No, I think that's a really great answer. I mean, very simply for me too, I think that in looking at the historic lineage of how that capital became flat, I saw that, I think that the material of ceramic, and I see it in the flat version as just underestimated, and decorative, I think now also in contemporary architecture is, that it's not particularly a good thing or a priority. It's performative as Joshua pointed out as a part of like how we judge architectural things in architecture. So being structural and being performative as a core part of that thinking system was, I thought we could go back to that medieval. I thought that they were more structural and more performative than what they are now. So
I just want to extend the question because asking why ornaments becomes performative in the contemporary practice. That's actually kind of touching a very fundamental issue to me because if you remember ceramic practice, terracotta practice 200 years ago, there was such a representation of something. So now that ornament is back in a way that we don't represent the angel, we don't represent the kind of philosophy or something. So then using all those kind of formidable, powerful technology, that ornament, new ornament, what does it represent? That's the fundamental question. And in that question, I believe that need of performative idea, sustainability idea is actually emerged to make up that answer. So then I think the fundamental question now is that looking at that fundamental this kind of change, that terracotta or ceramic itself is actually driving this change with the unique characteristic of the material and then the unique kind of idea of materiality. Is it really driving the innovation for itself, or the way we use terracotta is actually only the kind of overlay of bigger kind of trend, bigger agenda. It's only we use the terracotta to solve and to satisfy us the purpose. So it was kind of a fundamental question to me, like the kind of thinking of using terracotta versus using artificiality? Is it powerful enough to drive us to kind of introduce, innovate kind of different stuff, like more something new stuff?
Well, I think that terracotta offers a lot of interesting possibilities in that regard. One reason that it's very environmentally friendly to use terracotta is it is essentially dirt mixed with water that you then can create something that you can put on the building and use as a rain screen or some type of insulating system like trauma walls, things like that. So there's the environmental aspect there, but also terracotta has some very interesting properties that don't occur in other facade materials. For example, with steel, once you have formed the steel, you don't have much opportunity for rework. It's very solid, like same with concrete, things like that. What you put in the form is very close to what you're getting out at the end, whereas terracotta has a much longer workable life. So you can create shapes either with traditional hand pressing methods or extrusion, but once those shapes have been derived, you can continue to act on them and introduce a more, kind of reintroduce the craft or introduce more of a tactile sense to the material that you don't see in a lot of other materials.
I just want to say, I think it's a very perceptive thing to make that statement, that essentially, basically, we have potentially, if the caryatid, if the angel, whatever, if that's about terracotta as some conveyance of meaning, right, of philosophy, like we've translated that into something that's actually really more about performance criteria, that the ethos of our generation is really about issues of sustainability. I think that's an important thing to just state. And then what we do with that is still up for debate, right? Like, I mean, I doubt anybody, like I believe that we're kind of all moving forward following this agenda of sustainability, and we should, right? But I also think that clay and ceramic traditions have more to offer beyond just that. And I think that some of the historical references coupled with issues of sustainability makes it incredibly interesting. But I think I think that's one thing that will emerge from this kind of growing set of research nodes is like we haven't really figured out yet, like exactly what we're doing with it. Some people are kind of dabbling in one area more than others, but clearly, let's say like you're taking issues of potential meaning that come from nostalgia in a very clear way, right? Like so, nostalgia is like a different ethos from sustainability. Those two together, I think, can play against each other in kind of a really provocative way.
So, sort of a question for everybody. It seems to me that these questions of performance play out in interesting ways that might have some kind of feedback with the places where you're working. If you're working locally, you're looking at a German tradition, and you're working in California, that one aspect where, let's say, thermal performance or a kind of sustainability issue or strength start to come together is in the sourcing of materials, because sourcing of materials relates to different kinds of properties. At least that's my impression. And it seems like that's a place where some of the possibilities might be inflected a little bit by place. I don't know whether that's something that any of you have given any thought to. Obviously, when you're pressing through a die at great force, there's some relationship to the clay sourced locally. Slip casting is a different kind of animal. But I'm thinking like heat ceramics and Sausalito that is kind of known for its incredible properties, all having to do with material being locally sourced. Any thoughts on how these things feed back on one another?
Yeah, I'll admit that that's like out of all the work that I've been doing, however much I talk about materiality, like it's the materiality is basically clay
Yeah.
in some ambiguous sense of the word, right? And I produce everything. So most of what I've
geopolitical factors, but primarily being prominent because the two materials that come out of the mountains were the ones that first formed porcelain, right? So the Galilee Mountains, now we refer to that primary clay, one of those two ingredients as kaolin, which is sourced in Edgar, Florida, mostly, and all around, yes. So they come from lots of different places. Vernacular ceramics in this country is.
So I just wanted to probe a little bit further this point that Jane Young had sort of put out, but I think Joshua, you also responded pretty interestingly to. So we do have a turn of events with the use of the word performance. We know from our modern traditions there was a question of function, and function was probably more symbolic than it was performative. And now one can even argue that form follows performance is what you're arguing, right? At the same time, I think there's a question of another term that we're using pretty loosely, which is craft. And craft was a term that was fundamentally dismissed by the moderns because craft was not industrial. It was, and Bryce, Ariel, I'd really like to get your read on it also, because you, in some ways, spoke to that whole idea of touching and the haptic nature of this material. And that's sort of what the moderns were fundamentally against, the kind of representation of the hand at any point, in the industrial. Yet we use the word craft now as well. And is that fetishized, nostalgic of the pre-modern, or is that similar to what I would say, how we're using the term performance, which is a kind of a continuity of the modern project, yet in another term, or maybe a much more precise term. We're using the word craft quite a bit, digital craft. I mean, the two things seem so anachronistic. I'm just trying to think how you guys are thinking about the word craft now, as you're using it relative to that issue.
I'd say for me, sometimes it's easier just to avoid that word. I'm happy that it's back. I mean,
You're being tight.
it was way more radical 10 years ago. Now it's kind of everybody just accepts that as something that is a certain status quo. I think there's a theorist, David Pye, who's kind of like one of these theorists on craft, and some of you may know him or not, but he makes a nice distinction. He kind of also avoids the word craft, and instead he talks about workmanship, the workmanship of risk and the workmanship of certainty. And he basically says, like, it doesn't matter whether it's done by hand or whether it's done by machine. Like, the workmanship of risk is the one where there's a certain knowledge and expertise that allows for improvisation. And that's different from industry, right? Which demands a kind of, it demands breakability. So I think, like, in a way, the way that most of us use the word craft is that we understand that, it's like if you spend hours doing your scales on the violin, but then at a certain point you kind of like launch in, and you can get yourself in trouble, you can work your way out, and it would be impressive, it would be amazing. Right? And I would say that's what I value inside of that definition of the workmanship of risk, because it can be done by hand, it can be done by machine, all of those things are equally just to me. So that's the way that I kind of move forward in that question. It is important that we kind of get our terminology straight. But I would also say that it's like what becomes more productive, like the idea of risk in the kind of world of, let's say, design Darwinism, is that we want to just produce as much variation as possible, and that then kind of selection can come out of that, right? And so, in a way, you need to have the risk in there. Sometimes the risk is more easily produced by hand, and sometimes it's more easily produced by machine. I think that play is where we, that's what we have control over actually as designers, is to allow ourselves to produce more or less variation.
Josh, I'd really like to look over the tectonic horizon. Can you put your slideshow up for us somewhere? Thank you. some ways, Peter's explorations of, coefficient, putting numbers on it, he sort of defined risk envelope, that allows you to make whatever screwy shape you want as long as you don't exceed the tension on the wire. A lot of work now, Schumacher Associates, it's one big ornament. The whole building is a big chunk of ornament. And I think, so performative stuff may be trying to rationalize that just a tad. Positivism meeting with expression, whatever Shoemaker's term is. Back to the point of what Omar's going to brew the day, he's mentioned the lose to me, or Yolanda, that they're calling it neo-materiality in the sense that it's not dumb matter. It has its own predilections. The guy who's been running that extruder for 12 years knows that it'll want to hang right. It just does, especially if the extrusion is a certain shape. And you have to strap it in and keep it there. So I think there's a lot of interesting experimentation that can be done within the risk parameters, but also that would allow the expressiveness of the material to be worked with. Use others, graduates of the Ceramic Institute the workshop know that, but some of the scientists don't know that yet. All raw matter can be forced into whatever we need it to. Terracotta is sort of unique. The guys in the shop call it a living material. So that's why I want to look over the tectonic erosion.
So, unless Jim is super desperate to ask one more question, I guess.
Yeah, can I?
Go ahead.
Actually, to listening to that, maybe I'd ask a little technical question, which is kind of checking out, the limitation of the Terracotta itself. We never talk about it. So that, Peter, I was in the review. Once again, your work is amazing. And my question is, when you use the wire color, and then inevitably cutting the kind of holes in the kind of pre-form, because the Terracotta want to maintain certain depth. So that means when the wire hits the air inside of the thing, it creates a really sharp edge, which seems like kind of anti-Terracotta thing. So that, and even your kind of little simulation of the sound shows that holes in kind of sharp edges when hitting on holes. So is there a way you can avoid that? Like that wire cutting but maintaining the smooth surface?
Yeah, it all depends on what shape you're working with. So if you have something that has like a large blocking material, then you won't, and you're going to maintain cuts within that, and then you can plan it so that you don't have cells exposed, you won't have like little fragments. You run into certain drying problems when you try and do that. You have to really control it, things like that. But yeah, it really is kind of a two-part game where you're playing with the input of what your profile looks like, and then the different shapes you're trying to cut into it, and how the two things kind of come together.
So, well, actually, let me ask one wrap-up question for the whole group, maybe.
terracotta literally means fired earth. So terracotta is both a brick and it is an extruded panel, or it is pot spun on a potter's wheel. Like it is all of those things. It's just typically when you see terracotta used, the person who's applying it is picking one specific mode. Like you're looking to create a small sculptural piece, or it's going to be a whole facade, or it's going to become brick columns. I think that that's something that would be very interesting to explore, would be how kind of the different approaches to terracotta could maybe be combined, but I don't know that there are some examples. I think the one with the different shaped octagons kind of starts to look at terracotta as both structure and ornament, but there's not a ton of examples that I can think of that do that.
Actually, that scheme is supported by a substructure that.
Yeah, there's cables in it, right?
Yeah.
But the terracotta is supported, it's a
yeah,
weight in
there
there.
might be a degree of support, right? Because they are big pieces and so on. But I was, as you were talking, I was thinking, is there a use of the terracotta that is maybe reinforced and it's more structural? I couldn't think of any.
Just vault.
And
The vault.
the vault, yeah. But still, is it the material itself in small pieces? So it's all, again, it's the arrangement of the piece, but not a new system, like the concrete, reinforced concrete, where the combination of the two, the steel, the rebars, and they produce a new system, right? It still is, so, could be another step to explore, right, for the next colloquium.
I mean, I would say that exact, that territory between like architecture, like let's say ceramic componentry and some other form of structure, like that to me is kind of a little bit of a sweet spot in terms of where we get to innovate inside of architecture. And so in the examples that you showed today, and let's say even a larger body of Boston Valley terracotta in terms of what they do, my understanding, right? It's like it's kind of there's rain screens or facade systems, and then there's more or less like sculptural ones. Now the sculptural work actually is large enough that it demands structure, which then as soon as it's been parsed and built into componentry, automatically implies that it can operate at a much larger scale, right? So you could potentially have architecturally scaled projects that are more sculptural and performative, let's say in terms of a rain screen or a wind screen or sunscreen, than exists right now. Which to me that's exciting. So I think kind of like that in my guess is like where there's some real room for experimentation. Just both and.
Thank you very much to all the speakers, and thank you for the audience for sticking through what I've been picking out and seeing as like a blistering whiteness out there. I hope you all get